That seemed good. Great. So, hi, I'm Phil Trinder. This is work mainly done... Sorry. I'll be quiet. I forget that I know who I am.
Next up, we have Phil Trinder from the University of Glasgow telling us about the benefits of Tierless Elixir potato for engineering of Internet of Things systems. So.
The applause is for the confusion, right? So this isn't my work at all. It's done by Solaris Live, but she wasn't able to get a Schengen visa to come and talk about it. So I will do my best. Okay, IoT systems. My apologies. I know there are some people in the room who make their money out of IoT systems, but I'm going to do a quick overview. So basically, they're network of devices that either monitor or control the environment. So typically, if you think about the hardware, you have a bunch of these sensor node things that are distributed in space. Each sensor node is connected to a bunch of sensors or actuators that do stuff. So if you're in a drainage system, you might open valves or whatever, or you sense things like water levels. The sensor nodes feed data up to a server, and the server offers a web interface, typically, to multiple web clients. So you can think of it as a pair of distributed systems with a server in the middle. IoT software is a mess, conventionally. So I'm going to talk about a specific example, so it can be concrete. But it's absolutely typical. So the Glasgow Uni Smart Campus system, which I'm going to abbreviate as GUSC, is a classic room sensing application. We have the sensor nodes distributed in about 12 rooms in a couple of buildings in the uni. The sensors are also pretty standard commodity things. They sense light, sound, motion, temperature, blah. It's a Python-based implementation. It existed before we started working on it, and the sensor nodes are Raspberry Pis. IoT software is typically, like many distributed systems, it's implemented as a number of layers. So there's a perception layer where the sensor nodes live, and that's where you sense or change the environment. There's a network layer that communicates the data up to the server. The server does the application logic, whatever that is, also stores the data, usually in a time series database, and serves it to the web clients. The stuff in blue on the slide is the different languages and protocols being used, and these are the languages used in the original Python implementation of GUSC. And I'm sure you know that it's not unusual on the sensor nodes to be running nasty, nasty languages like C or C++. Sorry, guys. So the developers have to work in a whole lot of different languages. They have to be thinking in a bunch of different languages, and you lose the type safety that the languages have different type systems. They communicate with each other, and then what does a time look like in SQL? What does it look like in your sensor node? The code's splattered across a whole bunch of different files. In the Python implementation, there's a different file for each different sensor. So for the temperature sensor, they're classes. So you have a different class for the temperature sensor and a different class for the motion sensor. And you have to use these distributed APIs to interact correctly. Yeah.
Technical interruption. Were you using any of the industry standard protocols for any of this stuff?
MQTT is pretty much the standard protocol for interfacing from the sensor nodes up to the server. And you, well, we're using PHP, which is pretty much an industry standard. Horrible industry standard, but a standard. Okay. The alternative is to use a tierless language, sometimes called a multi-tier language, where you write the entire application as a single source in a single language, and you can then check what you might think of as client and server code for compatibility. Is the server is the client sending the messages the server expects, and vice versa? You generate the correct communication code, the compiler does, and because it's in a single language, you can guarantee type safety. This does require a pretty hairy language implementation because you have to generate the code, generate SQL code, and feed it over JDBC or ODBC or something to an SQL database, and generate the code that's going to run on the sensor nodes and send it to them. All of this stuff is pretty new. As far as I know, as we know, there are only 2 such tierless IoT languages. There are tierless web languages. You may know of Lynx, Phil Wadler's language. There's Hop, and the tierless principles are being applied in other areas where you try to combine essentially client-server code or other distributed code into a single source. So let me tell you a little bit about some of these tierless IoT languages. So Clean with itasks. Clean, to start with, is pretty similar to Haskell. I wouldn't say that in the Netherlands, but, and you're not allowed to say anything, Clements. It's similar in the sense it's purely functional, it's non-strict, it has a very sophisticated type system. itasks are an embedded DSL for so-called task-oriented programming. This is a way of building distributed interactive systems. I think they were originally developed for writing web applications, but they can also be used in other distributed settings, like sending tasks to be executed on sensor nodes. Persistent data in the clean world is maintained in something called shared data sources. These can be distributed so that you can read and write to a shared data source from a remote machine. And you can even, yes, that. Lenses are simply updatable views onto a database. If you think of SQL views. Okay. The second tierless IoT language is the Potato IoT library for Elixir. It was developed by Christophe de Troyer at Brussel, Vrije University of Brussels. It allows you to deploy Elixir code onto Beam VMs, remote Beam VMs. So if you have a Beam VM running on your sensor node, you can send it code to run. It uses functional reactive programming, FRP. That's essentially an event-driven programming model. Something happens in the environment, it generates an event, and you stream that event from the sensor node to the server, and from the server to the web client. To express that communication, you use the Creek DSL. It's unfortunately very imperative. It says, send this message. It's pretty cool, but one of the restrictions is because it runs on a Beam VM, it means that the sensor node must be relatively powerful. It has to essentially be a single board computer. Did I talk about that? I forgot to say that. Okay. Apologies. Okay. So let's look at the software architecture if you use clean. So C in the left-hand side stands for clean, and E on the right-hand side, ERS, is the Elixir, and I'll explain the rest of the acronym shortly. You have a single code base, the code, but different parts of that code effectively fulfills the functionality of the previous tiers. So the perception stuff in CRS is done using itasks. Those itasks in the sensor node, well, they write to a lens on the SDS. There's a network layer where most of the communications happens automatically in between the multiple tasks running in clean. At the application layer, you have another set of tasks. They also interact with the SDS and also tasks running in the web pages. ERS, that's the new thing that Solaris has built. In ERS, we run potato code on the sensor nodes. The Creek DSL is used to communicate back to the server. In ERS, the Elixir implementation of GUSC, the database is a Postgres SQL database, and we use Phoenix LiveView just as Clara did for her application. And Phoenix requires you to write some HTML. So again, the blue languages, the blue text are the different languages being used here. To explain those acronyms, we actually have 5 implementations of the same system. A key factor is whether the sensor node is a single board computer or a microcontroller. So microcontrollers are tiny little weedy processors, think like an Arduino. In fact, the platform we've used is something called a WeMOS. The full spec is in the paper. So PRS is Python running on the Raspberry Pi. PWS is Python, well, it's actually MicroPython running on the WeMOS. I'm not going to say much about the microcontroller implementations because the new stuff, ERS, is running on the Raspberry Pi. Clean, CRS, clean on the Raspberry Pi. CWS, clean on the WeMOS. Okay. So, what's new? Well, we now have an implementation of this GUSC little IoT system in a second tierless language, and we're able to compare that with Python to, we previously compared the clean implementations with Python and MicroPython. Now we can compare a different tierless language with the conventional Python. We can now compare 2 different tierless IoT languages. And the other thing Solaris did is we looked at the costs of managing failures in the GUSC system. So this is, as far as we know, the first analysis of failure management in a tierless IoT language. The metric we use in the study is source lines of code. It's a completely rubbish metric. It's a really bad metric, but we don't know anything better. And it's kind of useful for comparing multi-paradigm systems, and oh boy, are IoT systems multi-paradigm. You've got relational code in SQL, you've got imperative code, object-oriented, it's horrible. Basically, the idea is the more code you have, the more effort it is to write it, and the more faults you're going to have. Sorry, I'm going the wrong way. Okay, so the first results, concentrate only on the red boxes, please. Comparing Python, in particular PRS, with Elixir ERS, there's rather less code. It's about 87% less, I think. There's a lot fewer files, 3 rather than 38. And the only reason, I mean, it would be possible to put all the Elixir code in a single file. It's only 70 odd lines of code, but for modularity, it just works better in 3 files. Second message is there's far less semantic friction when you work in a tierless world. The Python developer has to work in these 6 different languages, whereas in the ERS world, there are only 3. We're counting Creek and Potato. Well, Potato/HTML, because you do actually write some HTML. Smile and nod, Clara, when you use Phoenix Live View. What's more, the Elixir stuff is more declarative. So the Python, you're in effect using 6 imperative notations and 2 declarative. There's a bit of both, and here it's 2 and 4. And being more declarative is probably one of the reasons the code's shorter. You've got less sequencing and other nonsense. Okay. In the code table I showed you, we'd analyzed by what the code is doing. So is it interfacing to sensors? Is it interfacing to the web clients? Is it doing communication? If we dig into that a little, well, one of the first startling things is you have a whole lot less code talking to the actual sensor devices, and this is because the circuits library in Elixir allows you to address them very directly. So the amount of code shrinks dramatically. The database interface also shrinks. The flip side is the FRP communication code is quite bulky, big, a bigger proportion of the code base.
A bigger proportion of much smaller code.
Indeed it is, yes.
The absolute number of lines, you get the same.
You can do the same again. You can look at the absolute number of lines, but it's a bit harder to digest. So here are the absolute numbers of code. So the communication code is almost identical here, but remember that, is less. But as a proportion of 75 lines of code, that's a lot. Okay, so summary, what did we learn? We think the fact that Elixir Potato is pretty much tierless is the key thing. There's much less code. It's more declarative. There's less semantic friction. And there are some cool libraries that really help for IoT stuff like talking to devices. And this chimes, it's a very strong correlation with what the clean study showed. Slightly bad news is the Elixir code runs in a VM, in a Beam VM, which is huge. From an IoT perspective, on the WeMOS, MicroPython runs in 20K. Full Python is 3.5 meg, and Elixir needs 21 meg. I will say something later about that, Pierre, honest. Okay. Look at the second thing, comparing two tierless languages. As far as we know, these are the only two Tierless IoT languages. What do we see? Well, one of the main messages is actually the size of the code bases are pretty similar, considering CRS to ERS. It's 10 or 15% difference. Elixir's database interface is really concise. That helps. And managing the nodes, provisioning code onto the remote nodes is quick, is concise, sorry, in Elixir. But Elixir Potato has significantly more semantic friction. Basically, you have to work in 3 different languages rather than 1. So Clean has taken this really radical view. You will use a single language. And everything is declarative in the Clean world. If we, again, analyze code percentages, feel free, John, to go back to the absolute numbers. We see that the FRP communication requires, because the communication is explicit, it's essentially almost entirely only 4 lines of communication code in the Clean world. Most of the communication happens automatically in the Clean world. So for both tierless languages, you generate a distributed system. Can't draw a sensible diagram of a system that has multiple sensor nodes and multiple sensors. So this is a picture of a system with a single sensor and a single sensor node. But this shows you the software deployment across it. And they're different. So in ERS, we have a single database on the server, whereas in CRS, there is an SDS, a shared data source, on the server, but every server node has what do I call those? A lens onto that database. So these lenses are replicated for every server node. And when you update this lens, the SDS, which you might think of as a master data repository, is automatically updated. And that automatic communication is a second communication channel between the sensor nodes and the server. 2 channels. Oh, and by the way, this is a UDP channel, and that's a TCP channel. Sir?
The flow of truth is from the local SDS to the
Correct. Information is flowing from the sensors. The sensors perceive the world, provide information. Oh, by the way, I2C is a completely standard IoT protocol, and all of the protocols, there's several different protocols used here are completely standard. Yeah, information is flowing right to left, and specifically these are streams, or this bit is streams in the potato world.
Okay, why then does it need to go across the top TCP channel and then down into the low and then across again? Why would it send data down that two separate
Yes.
TCP, the same data, presumably the same data, down the two TCP channels?
I don't think it's the same data. I think, I'm not sure exactly what is communicated here. Well, it's certainly the deployment of this task happens from the server onto the sensor node. So it's called provisioning. You send the code to be run down that channel, and if you can update it.
So that may be a bidirectional control channel, and the other ones are one more unidirectional data flow channel.
Yes, I think you're right. I think you're right that the lower channel is data. Okay, so when we thought about this, our conclusion was that clean iTasks is a pretty radical tierless language approach. It has really enforced a single language and paradigm. The downside is clean is a kind of niche language. It is used by some companies and organizations, but it doesn't have a very big software ecosystem. Elixir Potato is rather more pragmatic. You do end up managing more languages, and there is some imperative code, but the libraries that are available to you really help. Like Phoenix Live View and Circuits database interface. Questions, comments? Sir?
So I'm confused. Is Potato a library or a language?
It's effectively a library. I think Christophe describes it as a framework, but I don't know what a framework means. I think it's a library.
So it doesn't count as one of the languages?
We have treated it as a library, as a language, yes.
So, but if it's a library, you treat yourself unfairly then, probably.
Okay, so I think we took quite a strict view. In particular, we considered that MicroPython was different from Python. So it gets a bit grey when you decide when does a DSL when is a DSL different from a library? I think conceptually, actually, I would argue that Potato should be treated as a language because it has a different computational paradigm, which is FRP. And FRP is different from actor programming. So you're not sending mailboxes, you're not sending messages to mailboxes, you are rather adding events to streams of events. And so conceptually, I believe those are two different things, and that would be my justification over coffee.
So FRP is just upsell by another name, right?
It's very closely related. I would have to think hard to give you a careful answer to that. But
it's running, this is the bit that's running over MQTT.
Yes, correct.
Where could I find the Hello World example for Elixir Potato for a small project?
I don't know. Probably So there are a couple of papers, a couple of Christophe's papers, and I imagine that because he follows Simon Peyton-Jones' idea that you must have a motivating example, I expect Christophe has a Hello World example in his papers. Okay, so then the last thing Solaris did, and I'm going to tell you about, is looking at failure management in Tierless IoT software. We believe it's the first time it's been done. It matters. I don't need to persuade you of that. There are some IoT applications where it really does matter. So we did this in a fairly simple way. There is some simple level of failure management in the original PRS, CRS, and ERS systems, but we added 4 representative failures, 2 are hardware failures, sensor node, or any one of the 5 sensors can fail. A software failure, the software can fail on the sensor, or you can lose data on the UDP communication. And the way it looks on the web page is pretty simple. We added a status. So the web page normally just reports the 5 sensor values with a timestamp. Now we add a status of these different components, and guess what? The statuses change when things go wrong, like you unplug the sensors. So then we have 2 different code bases, the original ERS and then ERS with failure handling. So now we have some extra code doing the failure handling, and there's also additional code for talking to the database, because we've now got an additional table that records the status of the components in the system. The code goes up by about 71%. That's kind of what we would expect in a classical tiered application if you add that level of fault tolerance. There's 3 more files. We think it's better to think of the additional 3 files as 3 files rather than doubling the number of source code files. But actually, the absolute increase in code size is 53 lines. It's not huge. Clarence.
So, of course, the underlying idea of having these small projects that they scale to large. Of course, the underlying assumption is always that this is a small problem as well. Now, the question is, if you have a big problem, would this scale proportionally in the sense that you have twice as many files? Or would you have an original project with something like 500 files and then you also add 3 files for safety? Well, what's the truth behind that?
Good question, and we haven't, so this is an initial investigation. We haven't looked at scaling across, but you're likely right that, well, actually, who knows? I don't know what would happen with a bigger code base. If you ask me after a beer and I've had a chance to think,
Let's try that.
I may give you an answer. It may not be very good. A big piece of the additional code is to handle the failure of each sensor. There are 5 sensors. Even though you only write a few lines of code for each sensor, you'll end up with quite a lot of code checking the status of the sensors. I'm not sure that we learn a whole lot. There's now some new functionalities dealing with the failures. The database interface becomes more complicated. So really, I don't think we learnt anything surprising from this. It looks as though failure management in a tierless language is pretty similar to failure management in classical software. It's a single study of a small system, but it's the first ever study. And lots of the code is really boring. And no libraries to help us. Ho-hum. Okay, what did we show? Maybe I should do it slowly. Would you like it slowly or would you fast? We think there's more evidence here that tierless languages make developing IoT systems much better and far more likely correct and possibly even secure. If your communication has been automatically generated, perhaps there's fewer chances for bad things to happen. There is a big memory footprint, but help is on the horizon. There are these systems, GRISP, Atom VM. Hopefully we can start running Beam languages on small devices securely. As I said, we think clean iTasks is pretty radical. Elixir Potato is very easy to use, given the library's help. And the failure management is unsurprising. Questions, comments, abuse?
It's a very interesting topic, at least to me. So the potato DSL stuff, is it a sub-constraint of the Elixir stuff, or is it somehow I have to do? Okay, I probably just better go look at the code, right? But am I talking to this is it really different, or is it just a constrained subset of Elixir that I can only do like peek and poke of the sensors, and that's all it does? What's domain specific about it?
Potato is what I think of as a library for Elixir. It enables you to deploy code onto a remote VM and then to communicate with it. So that in the IoT world, that's called provisioning. So you provision sensor nodes, and it allows you then to communicate from those sensor nodes events, so stuff that's happened in the world, but what you're running remotely is standard Elixir code. So if you had actuators, if you had a library that enabled you to open valves or pumps or whatever, it's bog standard Elixir code that you've deployed. So it's pretty well integrated with Elixir.
I guess I'm going to look at the web, the GitHub. So.
The answer, I think, to Pierre's question, is it a different language? I think it is, because the paradigm is FRP. So it's functional reactive programming. You're thinking of sending streams of data. And I think you can probably send streams from the server to the sensor node. And you would need to do that if you want to send instructions for what that sensor, an actuator, should do. Raise the temperature of the room.
Okay, last question.
So this is more a comment than a question. There's been a little bit of work on tierless Haskell programs in Chalmers. So there's
Yes.
Haste, which is a tierless web programming framework. But there's something more recent that you can talk to Robert Crook about, who is here, which is a tierless Haskell for programming I think it's called trusted computing zone on some Intel processors. So there's a part of memory and so on which is protected from reading and writing from outside, and it's intended for holding passwords, etc., etc. And they have a cut down Haskell runtime system, and they can compile Haskell tierlessly to run on that and on the normal processor outside. So there might be something there that might be useful for you.
Yeah, yes, sorry. I'm not sure if I actually mentioned, thanks for the tip, John. I'm not sure I actually mentioned that stuff, but there's a whole lot of stuff. There's Haskell, which I think is also out of Chalmers. And there's Haskino that runs on Arduinos, and stuff. So there are kind of tierless things, but I don't think any of them are what you might call full stack IoT tierless systems.
Thank you.